Welcome to the next session. Today we will discuss photonic crystal fibers. A photonic crystal fiber is also called as a Hole fiber or Hall assisted fiber or, or microstructure fiber. Then it's named because it is named as a Hole fiber or Hall assisted fiber or microstructured fiber because of the presence of air holes throughout its construction. I will explain its construction later. There are two main classification of PCF. One is index guiding and the other one is photonic bandgap fiber. The first image shows an index guiding fiber and the second image shows photonic bandgap fiber. Let us understand the structure one by one. As we can see in the figure of an index guiding fiber, there is a solid high index core above which there are multiple air holes. While in the case of a photonic bandgap fiber, the cladding as well as core consists of air holes. In the high index core fibers, that is index guiding fibers, as the conventional type of fibers, the light guiding is occurring in the same phenomena, that is total internal reflection. As you can see, there are multiple air holes surrounding the cladding region. There are multiple air holes surrounding the core, that is multiple air holes are present in the cladding region. The presence of these air holes will decrease the refractive index of the cladding region. The refractive index of the cladding region of an index guided fiber is proportional, or it is determined by wavelength, the diameter of the hole, and the distance between the two holes, which is termed as pitch. In this figure, you can see that the light will be guided or confined inside the high index core of an index guided fiber, and the propagation is purely depending on total internal reflection. While in the case of photonic bandgap fibers, as we had already discussed, The core is also consists of a the core of a photonic bandgap fiber is also hollow. The photonic bandgap fibers, unlike the index guiding or conventional fibers, it offers totally a different guiding mechanism based on photonic bandgap of the cladding region. This mechanism allows guidance in a hollow core. See, as you as we just discussed before, that the core is also hollow. That means it is filled with air. So the refractive index will be lesser. So because of this photonic bandgap effect, the light can be confined inside the hollow region by multiple reflections inside the hollow core. Such air-guiding hollow core photonic crystal fibers can have a very low nonlinearity and a high damage threshold. They typically guide light only in a relatively narrow wavelength region with a width of say from 100 to 200 nanometer, and can be used for pulse compression with high optical intensities, as most of the power propagates in the hollow core. We have to arrange, or we have to create the cladding structure in such a way that the structure must be able to exhibit at least one photonic band gap at the frequency of interest. So similar to that of normal fiber fabrication, in photonic crystal fabrication also we need to create a preform. But the preform should consist of various capillaries so that we can create this microstructure. So as you can see the different stages, that is A, B, C and D in this figure. In the as a first stage, we will be creating individual capillaries. Then this individual capillaries we will arrange in such a way that in the case of index guiding fiber, the microstructure should be in such a way that we have to obtain very low refractive index, while in the case of index guiding fiber, as we had discussed just before, it should be structured in such a way that there is at least one band gap for the particular frequency we are interested, or the particular wavelength we are interested to transmit through it. After arranging these capillaries accordingly, we will create an intermediate preform. Later on, we will fuse this preform structure to the final preform, from where we can draw the optical final fiber from the drawing apparatus that we had discussed in our previous class.